answers to the electroconducting one?
Wait, what? I thought he said not to do it though.
I apologize for that mistake. It's okay, no harm done except for today. Hang on.
I'm actually very disturbed. Have you seen a psychiatrist lately?
Do my parents seem like the kind of people that take me to a psychiatrist?
Yes.
You'd be wrong. They're not going to pay for that crap. They didn't even pay for my... Never mind.
Okay, sorry, something has happened with my computer and I don't seem to have the answers. It's not that big a deal, that's not very hard, right? So, here you guys can tell me, what's the, number one, what do you got? You guys not do it yet? Or just ready to say it? 0.13 something EV? I would like the answer EV. You see that? Right? And if you do it in EV, you should not need scientific notation. There's a rule of thumb for like photoelectric effect scale stuff. If you do it in EV, it should be something that can be written easily without scientific notation. 0.13 sounds good to me. Okay. So if you didn't do that, check units. Probably the best way is just do it all in SI units and then convert to EV at the very end. Yes.
How do you translate columns into...
Click the button. Now type in Gmail.
Oh, coulombs. You can. I mean, that's so simply. But what you can do is just do coulombs is an SI unit. And so it's volts. So you just do everything in coulombs and volts and put an answer in joules. And then you can convert from joules to EV using the conversion factor.
That way.
1 EV is 1.6 times 10 to the negative 19 joules.
Okay, do that one.
So there you go. So if you have an answer that has a factor of like something around 10 to the negative 19 in it, then that's probably the issue.
Ooh, computer's warm.
What a surprise.
If you have something else, make sure you get 700 nanometer light that has to be converted into meters before you can use it, right? Make sure you did that. Okay, number 2. What do we have? Huh? 0.064? Really small. Is that right? 4 volts? Pretty good volts.
Oil.
I can work it out, but I mean, if the number's reasonable, you probably got it right. But there's not actually a lot of room for error. So, what about number 3 is about the piece of whatever it is? Sorry, I'm being really specific, aren't I?
Yeah.
Sorry, I have to look up something else. Yeah, it is, okay. So,
Why would you
so what do we have for 3, 4, and 5, and 6? Well, let's see.
piece of potassium?
Me too.
Maybe I should just actually do these because you guys seem unsure on that. But like, you probably did it right. There's not like, it's a simple equation. If you get it off, it's because of units, and then you're way off because of the units, right? So if you got a number that doesn't need scientific notation, you probably got it right. And I'll go back and double check these. I don't know, actually I have a guess what happens when you try and get too fancy with your technology. But this is the downside of the cloud, okay? Something overwrote something, I'm pretty sure. It happened earlier with your test scores too, actually. But then I have your test, so it didn't. I can give you these later ones. Let's see what's. I don't remember the order I gave them to you either. So the average kinetic energy depends on. The average kinetic energy depends on everything except intensity. That's right, because it certainly depends on the work function, right? The average, whatever the arguments that we use about maximum kinetic energy that we can measure, those same arguments apply to all the photoelectrons. And therefore, you should, whatever works for the maximum energy should also apply to the average energy. I don't know numerically what the average energy is, but I know that it will depend on the frequency for the same reasons. And if it depends on frequency, it's the same as depending on wavelength because they're related. And that means it's the same as depending on color because color is the same as frequency for light, right? Everything but intensity. Okay. Then for the next one, which statement best describes the observation? Best explains the observation? Sorry, they're all they start with. Yes, A. Good.
What?
And the next one is
Go down.
Don't know what to do.
I did. And you listened.
and the next one is
Really?
Yes.
Are you sure?
Yes.
E.
I don't believe you.
I don't believe you.
I win.
Okay. For the last one, there's
That scene
different
doesn't
answers you
change the
could
fate of the
give
universe.
that would explain it, but I think the strongest evidence that it's not just about some weird kind of wave that depends on frequency, energy somehow depends on frequency. I think the best argument that has to be particular is the existence of a cutoff frequency. Remember we talked about the cutoff frequency? When you go below the cutoff frequency, you get nothing, no matter how bright the light is. And so that's a case where it makes no sense no matter what, for any kind of wave argument. It only makes sense if each electron is being hit only by one photon. Then you can explain that observation. Right? The key, you can use other arguments. The key argument is that each electron is getting hit by only one photon. And that is what makes everything, make sense. Whereas in a wave, which is not localized, the energy would be distributed across many electrons. Yes? Is that 10? Yeah, did I skip one? Yeah, 10. Yeah.
Would it also be acceptable to say that like energy is transmitted in quantum
And you said energy is transmitted in quantum. That is not an experimental observation. That's a theoretical statement, right? You need an experimental observation, something that happens to explain it. See what I mean? So I told you energy is transmitted in quantum. You haven't seen that happen, right? Like you haven't watched the little packets of light fly by and stuff, right? So you have to give me an experimental observation. That's what I'm looking for there. Okay, so today we move into some serious quantum mechanics.
Oh no.
Yay.
For real. Wow. So
I want
that was kind of excitement, right? Ian?
Yeah.
So
I'm gonna die.
to do this, we need to get a bit mathematical. Here's why we have to get mathematical.
So confused.
Nah, not backwards, just linear. Here's the problem. In classical mechanics, in classical mechanics, all the quantities we work with are represented by what?
Numbers.
measurements.
Variables, right? Remember variables?
Oh, that's right.
There you have variables that represent quantities, right? And you have things like, m equals 5, and, and a equals 2, and therefore f equals 5 times 2, which is 10. And you can use them to solve for each other. So the rules that apply to the basic rules of algebra, right? I hope you remember how this part works.
Yeah.
Okay, good. So I pulled this out because we do it kind of instinctively. Oh yeah, well here's the thing. When you have a variable and you make a statement like a equals 2, what is the underlying assumption we're making about a that is no longer true? What's that? That it doesn't change, that it has a definite value, right? But in quantum mechanics, what do we know about the values?
They change.
It's not that they change, it's that they what? It's that they are not decided until they're measured. So before you make so this assumes I can solve for force and force equals 10. Then I can go measure the force and look, force equals 10, just like I said, right? Because it assumes that force has a value, a definite value, 100% of the time. But what we know in quantum mechanics is that before you make the measurement, the outcome is not determined, so it does not have a value. And therefore, the mechanism of basic algebra is not going to be any good for us. Because in algebra, it has a equals 2. We have no mechanism for a kind of equals 2 some of the time. Right? We don't have a equals 2 50% of the time and negative 2 the other 50% of the time. Right? So what we need is a mathematical framework that matches the quantum mechanical observations that we have. And this is not going to work. So we're going to need to make a new one. We're not inventing it from scratch, actually. This is all well established in calculus in math before the physicists got a hold of it, which is very useful. In fact, a lot of stuff that people thought would be kind of useless, like finding the eigenvalues of infinite dimensional matrices, which didn't really seem to be a particularly physically useful thing, actually ended up being really, really useful. So, this is just the key is here. So we'll start with the mathematical concepts, and then we'll explain what they are physically. So we'll have math, and then we'll have physics. Okay? So there's a math concept, and then there's the physical meaning of the math concept, right? Just like in class mechanics, the variable, that's a math thing, right? But you connect it to a physical quantity. The quantity is the physics, the variable is the math. You see? And you're used to just working with them so easily, right? But technically, the letter, that's a variable, that's the math part. It represents a physical quantity, though, and you make that connection to something physical. Okay? So we're going to do that here, but we have to do a little bit more. So, first of all, you have an operator. Okay, what is an operator? An operator, transforms a ket to another ket. You remember kets?
Yes.
So operators look like, for example, like a capital letter typically, like A. Is usually how I write it. So for example, if you do this, A applied to ket 2, you could get, so this is just an example, A applied to ket 2 can give you ket 1, for example. This is a possible operator. It takes some ket, and when you apply it to it, which just means A applied to this ket, you get another ket. Right? Now, it doesn't have to be that simple. It could be like something like this. Or something like that.
That looks beautiful.
Right? This is another possible operation. It just changes it into something else. Okay?
It's like
a function. It's similar to a function. It's not quite the same as function because these things are not quite the same as numbers. Okay? So we call it an operator because it takes these kets and it changes them into other kets. Okay? You see how that works though? And you can come up with rules that make them work and that's all fine. What an operator does is it's basically a transformation of, you can take it, you're taking things and transforming them to another state. Okay? In fact, another word they use for sometimes is a transformation or linear transformation. Okay, so that's an operator. So the next thing we need to learn about is an eigenvalue and an eigenstate. They go together. Okay. An operator takes things and transforms them, right? A way to imagine this is to imagine these kets as vectors. You guys study vectors?
Yeah.
Yes, sir. Oh, you have an MI4? What's that like? Okay. I don't know. I don't really know the MI series very well. Okay, vectors are, just think of them as arrows, okay? So if you imagine a bunch of arrows, an operator is something that takes those arrows and changes them in some way. You can make them longer, make them shorter, turn them, rotate them, reverse them, things like that. Right? It just changes the arrows in some way, in some predefined way. Like you get an operator that says, take every arrow and double its length. Okay, right? It just applies to all the different arrows. Now, I want you to imagine this room full of arrows, because it's kind of fun. So imagine this room full of arrows pointing all over the place, right? Okay, now, I apply an operator to it, it's going to be an operator that says rotate all the arrows along like this, around this axis. Rotate all the arrows by 180 degrees around this axis. So what do you see all the arrows do? Yeah, so the arrows start moving, right? So some of them pointing this way, they start swing this way, right? And some like this, and they swing this way. And all of them move around, they all rotate, right? Except there's some arrows that don't. If there's an arrow pointing straight up, you tell it rotate this, what happens? Nothing, right? It's still the same, right? So that arrow is kind of special, right? There's another arrow that, well, we don't need to go into it. Let's focus on this. Some arrows are special, okay? You apply the operator to them and they don't change. That's unusual, right? Usually you apply the operator and everything changes. But there are certain special ones that when you apply the operator, they don't change. Or in that you say they don't change much. They can change their length, but they don't change their direction. Okay? Another example is the arrows that are pointing this way, right? If you rotate them by 180 degrees, you end up with the same arrow but negative, right? That's another one. So there's certain ones that are special. They don't change, or you say they don't change much when you apply the operator to them. And so those are special things that we call eigenvectors. Let me talk about that. This is going to take a few times to understand. That's okay. We have time. So, I know you guys have lots of free time right around now. So, here's what the equation looks like. Okay. So let's explain what this is. What's A again?
It's an operator.
An operator. Good. So, this is an operator applied to some ket, right? When you apply it, the outcome is the same ket times a number. So this thing is an operator, meaning it's an action, it's a function. It's not, you're not multiplying by A, right? A is a thing that is happening to it. It's like a function, right? But this is just a number.
Wait, would you be able to say that A is equal to
No.
wavelength then? Because
No, you cannot say, that's not wavelength, it's just lambda, sorry.
okay.
It's a different lambda, it's not wavelength. No, you cannot just cancel those out because A is not a number. A is an action. This is more like f of x, but this is the notation we use, sorry. Right? It's like we have f of x equals x. You can't cancel out the x's. That's not how it works, right?
Unless you really want to irritate
Or
the
if you
teacher.
do, you're not doing very well on your math test. Just like when you have dy dx, you don't get to cancel the d's. Find dy dx. Oh, that's why it works. All right. So this is a number. This is an operator. They're different. So this is, like I said, sort of like a function. It's a thing that's changing this state into something else, right? But here, this is just a number. You're just multiplying by a number. So these two are different. And this thing is called, this number here is called an eigenvalue. And the special kets for which it works are called eigenstates, or sometimes eigenvectors. I give you both words because I interchange them accidentally all the time, because we use them interchangeably all the time. So I figure, I try to make myself not do it, but I always mess up, so I figure maybe what we used to. So eigenstates, eigenvectors means the same thing. Eigen is a German, word, well, German particle, I believe, right? Someone know German here? I believe it's like a reflexive particle. But like the rest of it is in English because we're Americans. So we take random bits of German and then smash them together with the English words to get things like eigenstates and eigenvalues, and eigenfunctions and all sorts of eigenthings you get in the book. So eigenstates are special, okay? Every operator has certain eigenstates that act specially. So here we go. Let's try this. Every operator has eigenstates, right? They're special, that they are distinct. Most kets are not eigenstates. There's a few special ones that are, okay? And those are your special eigenstates. Each eigenstate has a corresponding eigenvalue according to this function. If you apply the operator to an eigenstate, you get back the same state times the number. So whatever that number is, that is its eigenvalue. Yes?
If you care, eigen means own, so
Own,
it's supposed to
very
mean that each operator has its own special state.
It's an own state. Yeah, it's a state that comes back to itself. See? So it's like own, something like that.
Probably.
Probably. All right. My son has been like copying my like weird mannerisms. So now he keeps on saying like, he'll keep on being like, oh, I say something, and he's like, apparently. And I'm like, hey, wait. And he's like, and I'll say something, he's like, that's a good question. What? Like most of the time it's like not the appropriate time. He's not being sarcastic or anything, he's just copying what I say. And sometimes it's like at a very appropriate time. And I'm like, all right, kid, watch it. And I'm like, that's my voice.
Now you know how we feel, Dr. Dong.
So, and apparently, I say that phrase, apparently. I think especially to him, because he'll say something that makes no sense, and I'll be like, apparently. Anyway, so I don't expect you to have a full understanding of this after my brief description. Fortunately, what we do have on Moodle is a document. Do you remember that document that I sent you an email a while ago? It's called Direct Notation of Quantum Mechanics.
No, here you go.
I told you to read the first page of it.
Oh.
Now we're going through the rest of it.
Wait, we only had to read the first page?
But that's good. You're ready for this. That's right. No wonder that he's answering all the questions.
Thank you.
So that's good. I recommend you go through that a few times. Then work on the homework. Then maybe go through that. Like if this sort of thing takes time to sink in, right? To go through it. Of course, reading it blankly. Read it like kind of dumbly. Like don't read it like you read Harry Potter or something. I love Harry Potter, but it's an easy read. This should not be an easy read. It needs to engage your mind. But if you do that a few times, thinking about what it means, it will help reinforce it. Then I'll go over it here, and you have homework, and through all those things, we'll try and get it to really start to make sense. Gotcha.
Every operator has a state about eigenstates or
approximately yes, but we'll not deal with that. Yeah, no, they can be different. Let's just not worry about it. We're not going to get, sorry, that goes into linear algebra, and it gets complicated. It depends on the dimension of the vector space, basically. So we will not get into that. Dr. Hawking was way more into linear algebra. I try to avoid doing that because I think it's crazy. Yeah.
I'm a bit confused why like an operator on an eigenstate can be the same and number from an eigenstate.
Right. So here, let's think of it this way. Let's take the function f of x equals x squared.
Okay.
Right? For most numbers, f of 2 equals 4, f of 3 equals 9. You get different stuff, right?
Yes.
But f of 1 gives you 1. It's a special point where the function gives you the same thing back, right? There's one more. F of 0 gives you 0, right? So these are special. Why are they special? They're not special because like 1 is so magic, right? It's just that there's some point where this happens, right? There's some point where this works, okay? It's kind of like now. Operators are not the same as functions, okay? And so the analogy is not perfect, but it's something like that. There are points where this works, right? Not because B is super magic, right? Just because that's where this operator and this state line up, just so that you end up with the same state. It will only happen in specific places. And specific functions, I say specific texts, will only certain ones will work. Okay, and the other ones won't. So it's a very rare thing, so it's a special thing, but it's not like magic. It's just that's when the numbers line up right. Yeah.
Does the operator have to be there for the eigenvalue to correspond to eigenstate?
Yes. So each eigenvalue, so operators give you the eigenstates, each eigenstate has an eigenvalue, so they all kind of go together. And this is the equation that relates them all. Okay. If you can understand how this equation works, you'll be in good hands. Yes? What a great question. We haven't got there yet. Well, let's get there now. Okay?
What would it look like if you had an operator that didn't yield an eigenstate?
I don't believe that is possible except in the case of the null operator, which is kind of trivial. Or maybe there are everything I forget. this is a linear algebra thing, but I believe all operators, all linear transformations and normal behaved things, sort of normal physics, will have eigenstates.
Okay, so in the case that's on the board, like A at B at equal to lambda,
Right.
you could like replace lambda with any number, and that would imply that that particular thing has an infinite number of eigenvalues.
Right, but we're not, because this is the generic form of it, but for a specific operator, right, this is actually represents a mathematical operation. And this has to be a very specific thing that it's operating on. And you will get some well-defined output here, right, that will not usually look like this. And only when it looks like this do you call it an eigenstate.
What is this in particular as opposed to that?
Could you just like...
Sorry, only when it looks like the exact same cat. So here,
only when it's the exact
so
same.
here, not an eigenstate. 2 is not an eigenstate of A. Why? Because when you apply A to 2, you do not get 2 back.
Oh, okay. So when it's
1 is not an eigenstate of A, because when you apply A to 1, you don't get 1 back. But, making this up entirely, but let's imagine you had this.
Oh, well, look at that.
Now this one's an eigenstate. Why? Because you get back just 3 times some number. Do you see? So you will end up with A applied to something, but when they line up, so when they get the same thing back, then it's an eigenstate. And the eigenstates are very special.
Then would the eigenvalue be 5?
Yes, very good. Then the eigenvalue would be 5 here. So. It is possible for multiple eigenstates to correspond to the same eigenvalue. Yes, that's called degeneracy. Is that a weird word for it? Yeah.
How does this apply to the quantum mechanics aspect?
What a great question. Let's get there right now. How about that? But it is good. You have to understand the math before you can understand the physics.
Is that a phrase your child says often? What a wonderful question.
Yes. Yes, he does. As a matter of fact, he does. Apparently. And it's like cute and kind of like, oh, why are you saying that? His Chinese is awful now. His Chinese is worse than mine now. He used to be substantially better than I was, but he very deliberately lost it all. He can still understand it, he just pretends not to. It's quite clear he understands it. When it's about like food or something, you're like, because we still speak to Ezra in Chinese, just kind of recreationally, I don't even know. And just like the sad attempt that maybe he'll learn a little tiny bit from it or something. Anyway, but if I'm like, Ezra, and he'll be like, oh, I want to eat. So anyway, no, he used to pick up a thing from us, and he'd say, do you guys learn Nishiang De? So it means basically in your dreams, okay? It's basically Chinese for that. And back when we spoke to him in Chinese, he said like he wanted to go, it's like he wanted to stay at our house forever. And he would ever say, right? Because my wife's mom says it all the time. It's like, she's kind of sarcastic too. So he said, anyway, then he started saying it, and then he was in like Sunday school, and his teacher was like, okay, woman after shoot, right, we're gonna go outside, and she's like, Nishan. She blamed it on my mother-in-law. And we're like, no, actually that was us. Okay. All right, so let's talk about it. Each of these corresponds to things. So here we go. An operator corresponds to a measurable quantity. This is a little bit tricky, so let me give an example here. Okay. So someone give me an example of a measurable quantity.
Energy.
Energy, great. That's exactly right. That's what I mean by a measurable quantity. It's not a number, right? But a concept of a number, a quantity, right? Something that you can measure. Okay. An eigenvalue is an actual measured number. So someone give me an example of an eigenvalue. 10, great. So, for example, you can have an eigenvalue of 10. It's an actual number. You don't. No. Too late. The die is cast. So, an eigenstate is the state corresponding to the measurement. This last one is the hardest to understand. It's not actually that difficult. So you might write it something like that, for example. And you're like, huh, okay, this one is probably better done with an example, so let me give you an example. Actually, first of all, this thing, this is important to know. Wave functions are represented as jets. Yeah. What a great question. How about I answer that? Remember, a wave function is not an answer in itself, right? Remember I mentioned wave functions cannot be measured directly? Or is that the other class? Anyway, wave functions cannot be measured directly. Because what do we do with the wave function? What did it tell us? It tells us about probabilities, right? So you use a wave function to extract probabilities. So just having a wave function is not a physically measurable answer yet. You need to have a probability, then you can measure a probability by doing it a million times and seeing how the probability comes out, right? So, so to actually get this to something measurable, we need to get a probability. Our answer is a probability, okay? So here is the most important part that you have to remember. And if you don't remember this part, then you miss every question on the quiz, and we're both sad, okay? So please remember this part. It is different, it is very different from how you do other kinds of physics, and even other problems we've done so far, and it's extremely important. So here it is. The probability of measuring particle in state psi, so that's its wave function, psi. I'm sorry, let me modify something. A particle, sorry about that, with wave function psi. Okay, so what this wave function is psi, that's its current wave function. To be in state, to be in state A is, okay, so before I tell you the answer, right now, psi is the state of the particle, the current wave function of the particle, right? I want to know what's the probability that it's going to be in a certain state A. Okay? You know that answer is usually not a definite thing, right? It's going to be some probability. You want to know what it is. Here is how you calculate the probability, most important thing.
What?
Okay? It is the bracket of A with psi squared. So that's what you use the raw for. This is so important, and we'll put a red box around it. And stars. And
if you have stars, there's also planets.
Planets? Wow, that's hard.
Make sure you don't forget Pluto.
That's not a planet. I don't think the planets are working well for me. But here's radiation. All right. So this is really important. Okay. This part of the unit can be confusing because I often ask you a lot of different questions to push in different mathematical things. But at the heart, whenever I say, what's the probability, which is our final measurable answer, basically, is what's the probability, you calculate it like this, right? So you take the wave function, you take the bracket with the state you're interested in, and then you square the answer.
Wait a minute.
And wait.
Didn't you say earlier that if A equals B, then the bracket of
Right.
A equals 1, and
right, but
so you're saying
remember
that it's
I
always-
also said there was that rule that said you had to kind of break it down into basic things first. I'm able to explain it a little bit now. I mean, that rule only applies if they are eigenstates of the same operator. I will, and let me show you this in example first, and then maybe that'll help. Do you have a question, Jay?
How do you evaluate climate?
So you have to be given a lot. So let's do an example. Let's say we have a new student visiting. we have like a new student coming to class. So, what might you be interested in about the student?
Age.
Their name is for it. Age, okay. You might be interested in the student's age, right?
Their political
you know,
beliefs.
and I used to do this example with age and with their sex, but then that became a political issue and it got confusing, so we're moving on from that. We're not doing that one anymore. So let's do grade. Grade's easier than age, okay? Because it's nice and easy. There's only 3 possibilities. What are the possibilities? Okay, so what we have is a grade operator G, right? That's the grade operator. Remember, because every physical measure of quantity corresponds to an operator. So our grade operator is G. Okay? And what are the eigenvalues if I make measurements of the grade? What are the possible eigenvalues of grade?
The actual grade, so like 10, 11,
good.
12.
10, 11, or 12 are the possible ones you can measure, right, at this school. So, the eigenstates then, there would be 3 of them that correspond to the 3 eigenvalues. You can call them whatever you want, but I'll call them, just as this example, I'll call them sophomore, junior, and senior. Because why not? You could, of course, call them Cat 10, Cat 11, Cat 12, but some people get confused by that. So I'll label them with birds just so you can see. Okay? So these states represent the actual states that that person could be in. Could be a sophomore, could be a junior, could be a senior, right? As in real life, you cannot be both a sophomore and a junior. You're either one or the other, right? They're exclusive. But since this is quantum mechanics, before we have measured this person's grade, then it could be indeterminate. Right? Right. So let's imagine that I tell you, this is the sort of thing I would have to tell you. Let's suppose I tell you that the wave function of our visiting student is, let's do, okay, good. I've given you a wave function for the visiting student. Do you see what the wave function looks like? It looks like the combination of kets, coefficients times kets. Sorry, I'm using the wrong kets. Let me use the right kets. I bet. Let me be consistent here. Sorry. Yeah. Okay, so this is the wave function of the visiting student. Because we have not made an observation on this student, we do not know, not only do we not know what grade the student is, but what did you say? They don't have a definite grade yet because we have not yet made the measurement. Okay? Yeah.
Why is it like, why couldn't it be 1/3, 1/3, 1/3?
That one wouldn't work, and I'll show you in a moment. But this is just a sample one work. Okay? You'd have to be given this at this point.
The function itself isn't representing the probability, right? We have to find the probability through that.
That's right. We use the wave function to find the probability.
Okay.
That's right. And let's do that. So let's say, what is the probability of being that the student is, pick one,
Junior.
sophomore?
Oh.
None of us are sophomore. Okay, so we say, what's the probability of our visiting student being a sophomore? Okay, now we apply this. So tell me, what is the expression I have to write to find the probability of being a sophomore? Go for it, Benji.
The bracket. Is it just bracket?
Bracket, yeah, bracket.
The bracket of sophomore and what's the term? Phi?
Psi.
Psi. Squared.
Good, very good. This is what you have to write. You see, we want to know what's the probability of sophomore. I already know the wave function, so that goes here. So the ket has the wave function in it. I already know that. And that thing's pronounced psi. I want to know what's the probability of being a sophomore. So So the thing that you want to know about, that goes in the bra. And so you get the sophomore bra, the side ket, and then you take the bracket and you square it. Let's do that.
Yes, please.
Okay. So, substitute out, always work inside to out, right? Squaring should be the last step. Squaring is the very last step. But don't forget to square. Always someone forgets to square. Don't forget to square. You'll get silly answers that are like negative or imaginary and things like that. You can't, but if you square it, then everything will be fine.
Everything's pretty.
Remember, this is the probability. If you square it and you get a negative number or a complex number, you mess something up, right? Probabilities don't do that. And this is mathematically guaranteed to be a number greater than 0 or greater, a real number. So that's how. Okay, so here we go. So this is the sophomore bra with the wave function. I'll just write it all out so you can see it. Okay. Now, all we have to do is take the bra and distribute it.
We can do
across
this.
the wave function. Okay. Now, you can do this fast. I'll go slow this time. We'll do fast. We can do it fast later. So remember, when you do that, it's really easy. You put the bra next to the ket. You multiply any coefficients, and there's no coefficients on this one, so it's pretty straightforward. So you just take this coefficient, move to the front, so you get 1/2 soft bracket soft plus 1/√2 soft bracket junior plus 1/2 soft bracket senior. Okay, now the rules that I told you about zeros all going to 0 or 1 only work when they are all the eigenstates of the same operator. So in this case, sophomore, junior, senior, right? Those two work by the rule that, for example, soft with soft equals 1, whereas sophomore with junior equals 0, okay? They work when you are working with the eigenstates of operators. Psi is not a single eigenstate, it's a collection of them, right? Therefore, you don't get to just call that 0, that's not how it works, right? You have to break it down into the eigenstates of the operators, then you can apply that. Now that they're like this, now you can say, what's soft bracket soft? 1. What's bracket sophomore junior? 0. And sophomore senior? 0. There's no like weird commentary going on here, by the way. And so, what do we get as our answer? Inside we get 1/2 is all that's left, right? If you go to 0, this is 1, so you just get 1/2 quantity squared, so 1/4. So what's the probability of measuring the student to be a sophomore? It's 1/4, right? So 25%.
Why is it 1/2?
If you evaluate for all of them, you'll always have for one.
It had better.
No, I mean like, oh, because it's 1/2 times 1. Don't call.
Well, why don't I answer both those questions for you? Why don't I answer both those questions?
What if we do 1 over the square root of 3?
Okay, hang on. Slow down here. Okay, first of all, we can now go a little bit faster. What's the probability of being a junior? Well, it's the square of the bracket of junior with psi.
Wouldn't it just be
Right.
1 over 1/2?
So
yeah, 1/2.
we should be able to do this a lot faster now, right? Because you're just going to do the same thing and distribute it over these. But both of them will give you 0, right? All except for which term? The junior term, right? So what are we going to have inside this? We're going to have 1/√2
Squared.
squaring it. So the probability of being a junior is
1/2.
1/2. Neat, right? What's the probability of being a senior?
1/4.
Well, yeah, you can already see it because you're going to distribute senior across this, right? And these will give you 0, this will give you 1. And so you'll end up with 1/2 squared, which is 1/4. And oh look, 1/4 plus 1/2 plus 1/4 adds up to 1. Yes?
What if I is like a function? Weird, crazy thing.
Okay. Psi, good news for you is that quantum mechanics is a linear science. All transformations in quantum mechanics are linear. zero, that means is psi will only ever be coefficient times something plus coefficient times something plus covariance. So you don't have to worry about other cosines and stuff.
So it's helpful. Or just Eric, will we like do that like it? What the code is?
Yes.
Yeah.
So let me talk about that. I think a lot of people have questions in that direction, so hang on. Let's talk about it. Let's say I do what someone said once. Let's say I write this. Sorry. This is not that. This is what they said. Okay, someone has suggested this at some point. Okay, good. Tell me the probability of being a sophomore. Well, you would take the bracket of sophomore with psi, and if you do that, you know that sophomore, that will give you 1, and those will give you 0. So you'll end up with 1/3 squared, which is 1/9. Right? And then probability of junior would be also 1/9, and probability of senior would be
1/9.
also 1/9. And so you sum these up together, 1/9, 1/9, 1/9 gives you
3/9.
Oh, not 1. Okay, what does that mean?
That means there's something we haven't accounted for.
That means something is wrong with your wave function. Okay? It is the wave, that means the wave function is bad. Because the wave function does not, the different sum of the different probabilities needs to add up to 1. If it doesn't make any sense. Something has to happen, right? You have to measure something when they show up. And so, therefore, this is a bad wave function. So, how do we fix the wave function?
Is there a way to know if a wave function will work?
So there's a way to fix the wave function. Sorry. The way to fix the wave function is to normalize it. Okay? And normalization means the sum of all probabilities is 1. It must be, or else it makes no physical sense. And therefore it cannot be used as anything in physical theory. Okay, so that's a requirement, okay? How do we normalize? Well, let's say you have this, the first wave function I showed you was normalized because all the probabilities added up to 1. This one is not normalized because those probabilities do not add up to 1. But you can take a wave function that's not normalized and normalize it so that it all adds up to 1 properly. And here's how you do it. Another way of saying this is a normalization condition that looks like this. The bracket of psi with itself must be 1.
Well, didn't we already? Never mind.
Remember, psi's not an eigenstatement.
Oh.
So that actually is a non-trivial statement. Okay? So the bracket is, the way you normalize a wave function is you take, I guess we can start with that one. Well, let's do, yeah, whatever, sure. You can start with that one. So here's the wave function. We know this one's not normalized, right? So what we're going to do is multiply the whole thing by an unknown constant, A. Okay? And now I'm going to find an A such that it's going to require this normalization condition to be true. That's a bracket psi with psi equals 1. To do that, first I need to write out what the psi rod looks like. And what would a psi rod look like, really? Okay. And so we get soft. The good news is, remember how you switch from kets to bras? Yeah, you take the complex conjugate of all the coefficients and you flip everything. And there's no complex numbers here, so we're fine. Okay, good. So now I can take the bracket of psi with itself. Okay, according to this, that would be well, I'll write it out, why not? You don't have to write all this out if you don't want to. Times A third psi. all we have to do is work this out. Now these a's are both constants. The constants all just go to the front, right? So here's an a constant, that becomes a squared. Now, there's going to be 9 terms, but I'm not going to write them all out because most of them go to 0, right? So we can go a little bit faster. Sophomore goes with soft, that gives you 1, right? So we have 1/3 times 1/3 times this bracket gives you 1, so that's 1/9. Okay? Sophomore with junior gives you 0. Sophomore with senior gives you 0. Junior with sophomore gives you 0. Junior with junior, right, when they're the same, that gives you 1. So here we go 1/3 times 1/3, so 1/9. Junior with senior gives you 0. Senior with sophomore gives you 0. Senior with junior gives you 0. Senior with senior, that gives you 1. So again, 1/3 times 1/3, which is 1/9. So we end up with these three terms added up. Do you see what I did? We've done this kind of operation before. I did it a little faster, so I didn't have to write out all those 9 terms. Most of them go to 0. Okay, well, 1/9 plus 1/9 plus 1/9 is 1/3. So I have 1/3 a squared. This is side bracket psi. What's side bracket psi supposed to equal? 1. So I say 1/3 a squared equals 1. Therefore, a equals √3. Okay? Now, if I go back and put this in my wave function, that means my wave function psi equals √3 times 1/3 soft plus 1/3 junior plus 1/3 senior. Yeah? It certainly could be negative √3. It could be √3i. It could be a lot of things. But the fact is, it's not really worth doing that. There's more than one possible value of a, but as long as you have one that works, you should use it. So you typically just take the positive root. Yeah.
There's a side bracket side.
Right. You take the bra, multiply by the cat, and that gives you the bracket. Yeah.
So this is like the eigenvalues being 10, 11, 12. What is that?
It does not show up in these equations. So what you know is that the sophomore cat corresponds to an eigenvalue of 10. The junior cat corresponds to an eigenvalue of 11. This one corresponds to an eigenvalue of 12. Right? The numbers 10, 11, 12 do not show up in this wave function. That is external knowledge. You know that if you measure it to be in this state, that's the same as measuring a grade value of 11. Yeah.
So like relating that to what so would it be like cat soft equals 10 cat soft?
Yes, that's correct. Given what I told you, the grade operator times soft would equal 10. Soft, like that. Right? Because I told you the eigenvalue was 10 and that soft was an eigenstate. Okay, good. Well, these are among the blankest expressions I've seen all year, so that's good. So the best thing to do, I think, is to go through it again, and then again, and do some problems, and then go through it again, and eventually it will start to make sense. This basic thing where you find the probability, that's the most important part, and it's not that hard. You should be able to do it pretty easily. Just remember to square it. Okay? And then everything else just takes a little bit of practice, a little bit of work to make it to figure it out. Yes.
So where did you get that G operator?
That was, sorry, I just erased it. That was what we started with, remember?
Yeah,
It was
no,
a
I
grade
mean,
operator.
like, where, okay, I'm sorry, like, where do you get the 10?
The what?
Like the 10.
That was a requirement from what we set up. There's an operator G. It measures, it has eigenvalues 10, 11, or 12. And this is the equation that defines an eigenvalue, right? So that this is true because I said it must be true this way. It is possible, of course, given an actual operator, to actually find the eigenstates. That is well beyond the scope of this class. You'll do that in linear algebra. And we're not going to do that in this class. Yes?
For the 1/3, 1/3, 1/3, is those, can you stick anything in those and you'd still be able to normalize it?
Yes, you can put anything there, unless they're all 0. You can put anything in there, and it's always should always be possible to normalize by using this method.
Okay. And it doesn't matter, it doesn't affect the actual wave function itself.
It doesn't affect the relative proportions of each. It just sort of scales them all so that the total is 1.
Okay.
Yeah.
Like wave functions are composed of cats can be other wave functions?
The wave functions decompose of other wave functions. I mean, kind of, yeah, sure. We don't do that. I mean, it's not as weird as you find. They're just functions, right? So yeah, I mean, so it's nothing fancy. But in the end, they all end up looking something a lot like this. Okay? Because they all have to be linear. So they all end up just being coefficient times coefficient times kappa.
You just use that root 3.
Yeah, absolutely, you can. In fact, what would you get on each? We just want for root 3 for each, which is what would make sense. By the way, please don't rationalize your denominators in this unit. Rationalizing denominators will make it actively difficult. Like, actually worse than leave them unrationalized, please. 1 over root 3 is much clearer than root 3 over 3. Okay, I will give you some homework. It's important.
Okay.
So focus on it. Work on it. I know you have nothing else to do, right? So focus on it. We're going to try and understand some very important stuff.